Applications and influences are always important to consider, of course, in any water treatment system. For UVC, the most important one is the UV dose. This is a product of the intensity of the lamp, the time you illuminate your organism or your target compound, and how the water flows through the reactor. I'll get to that later. But the intensity and the exposure time together produce a dose in joule per square meter. You see the value there. And within constraints, the same dose in the same application, you can expect the same effect. So if your dose, for instance, for disinfection is 300, you can expect every time when you apply that dose of 300 joule reliably to reach a comparable effect in disinfection. But of course there are constraints. If you use raw sewage water, you will have more trouble disinfecting it than ultra pure water. But dose is one of the main parameters to consider. And that's quite easy because you can get tables of microorganisms where they say, for instance, for E. coli, you need a dose of 45 joule to do 1 log removal. And 1 log is 90% removal. That means if you have a system of around 200 joule, you can do 5 log removal. And it differs per bacteria, per organism. Viruses in general have quite a high UV resistance. Algae even higher because they generally live in sunlight. Sometimes even UV light can make them grow, which is very important to consider if you're designing or integrating a UV system. And in general, you can say the smaller the organism is, the deeper it is in the ground or your body, the more sensitive it is for UV light, which is logic. As you can see, for instance, yeasts or fungi or protozoa and algae, which are more complex, larger organisms, in general have a higher UV resistance. And we can walk in the sun and nothing happens, which is, of course, quite logical. Next to just the dose, which is important, this is the amount you need to kill something, to put it bluntly. It's also very important how dose is distributed through a system. UV systems we make generally reach a log 4 to log 5 disinfection. That means 99.99% of all bacteria are killed or inactivated. This also means that every drop you're not treating well can make your system go from a log 5 reduction to a log 6 reduction or to a log 4 reduction. Because that last drop you don't treat contains enough bacteria to go from 99.99% reduction to 99.999% reduction. That last 1,000th of a percent is quite important. So that means you're not looking just at your average UVC dose, but the minimum of your UVC dose, the part of your water that goes through the system untreated to some degree, is very important. And this comes back later in the presentation when I talk about system design. How do you design a system so your minimum is as close as possible to your average? We discovered this also 20 years ago, 25 years ago in our company when we made a system, and it didn't really matter how much more lamp energy we put in, we couldn't reach more disinfection. So we started modeling it, and we came to the conclusion that system had a really nice average dose, but the minimum dose was too low. So the part of the water that wasn't treated was large enough and untreated enough to really limit the disinfection. We made a change. We went from a side stream input to an axial inflow. I'll show pictures later. And that really improved the minimum dose. And then we integrated a special flow plate that makes your water stream controlled along the UV light. And that increased the minimum dose further. And this is an ideal case, or at least a case where you want to be as closely as possible, because if your minimum dose is very close to your average dose, it means you can save energy because you don't have to use more UV light than you need, and that energy your lamp uses is transferred almost homogeneously through your flow. So every watt you put in, you use for disinfection. Another thing that's very important for UVC light is transmittance. We can't see UV light, so we can't also see from a sample if it will block or not the UV light we use. So we have to measure it, and many organic compounds absorb UVC light. So a sample might look very clear to the eye, but still contain enough absorbing compounds to have a really low UVC transmittance. And that means the UVC light is penetrating less deep into the water. You see a visible example here, where here you have a really low transmittance. So the light stops already halfway through your cuvette. Here you have a really high transmittance and all the light permeates through your stream. If you imagine there's a lamp here, in this case you can only make a really thin UVC reactor. If your transmittance is high, that same lamp illuminates a much larger water volume because it penetrates deeper. And that's very important. It doesn't mean you can't apply UVC here. There are systems here too, but they're designed differently from systems that are made for this situation. And you do it in your reactor design, in your volume you're treating. And an important thing to note is edge cases are really important. Transmittance is expressed as the percentage of the water that goes through the water in 1 centimeter. So if your transmittance is 90%, after 1 centimeter, you still have 90% of your water left. So it's the opposite of absorption in a way. And these edge cases are important because if you have 99% transmittance or 98% transmittance, the absorption from 98 to 99% halves. So from that perspective, these last percentages at the top and at the bottom are really important. But it's more to understand how this works. Because in general, a good system should be defined at a transmittance, for instance, 95% and up, where these last percents are not your biggest influence. Because you can understand, for instance, if you make a drinking water system and you make it specifically for 98%, where you need to reach a certain amount of disinfection, that drinking water is not always 98%. It will be between 90 and 100 sometimes. It will go up and down. And that means if you really go to these edges, that if the transmittance drops a few percent, you can't guarantee your disinfection again. So from an engineering perspective, it's important to know this effect, but it's also important to consider where do you apply the UV and is the range you use safe? You can easily calculate the most efficient application, but safety, especially when you're disinfecting something, is more important. There's another value, a value you might be more familiar with, turbidity. Turbidity is a measurement of particles. It's also a light measurement, but it measures something really different from transmittance, which really measures absorption of dissolved organic compounds in the water. So quite often we have customers that ask us, we have this and that turbidity, what UV system should we use? And we always reply, well, we actually need a transmittance because turbidity and transmittance don't correspond one-on-one. And why this transmittance is really important? Firstly, you see a number of water qualities. Wastewater in general has a really low transmittance. It's really dirty, it's quite logical. Surface water is very variable. In the Netherlands, it's generally around 40 to 70. If you go to the Swiss Alps and you have really nice, pristine mountain water, it will be 90 or even more than that. It also correlates really strongly with dissolved organic components. Processed water is also quite variable. Drinking water in the Netherlands is between 80 and 95. Pool water is generally one of the cleanest waters you'll meet from this perspective, because it also contains chlorine. So in that perspective, it's not that clean, but the transmittance is really high. Ultra pure water, of course, generally has a transmittance approaching 100% because it contains almost nothing. Here you see the transmittance going up from 0 to 100. And here you see the two lines of two example systems of us where you want to reach a certain dose, 200 or 400 joule. And as you can see, especially in the upper range, your capacity goes up really quickly when your transmittance goes up. So it also means you have to make the system fit for your transmittance. Other application considerations are also important. This is a system we made to use under the sink in hospitals to avoid antibiotic resistance, to breathe in the siphon under the sink, which was a new application in a research project. And then you also have the other applications. You want to treat the water, but you also want to treat the air above it. Can your lamp handle that? Can your quartz sleeve handle those two areas? How often does the water stream through it? Are there other things happening? Does the light not come out of the sink? You want to treat for Legionella in some cases. In surface aquaculture, you have salt water to consider, which behaves differently from sweet water. And for instance, in fountains, you have a closed loop, generally with a spraying apparatus. So the water is aerated. And for each of these different cases, other engineering aspects need to be considered to make a system that fits that application.